Thank you, organizer, to give opportunity to present in ISDA convective scale data assimilation. So I am Dr. Ashish Routray from NCMRW, and good morning and good evening to all of you. And this work is with help of my junior colleagues and friends at NCMRW. So I acknowledge also them. So here my topic is develop rapid update cyclic data assimilation system for prediction of severe convective weather system. So we have developed two type of HRRDA system. So one is NCM based HRRDA system that is based on resolution 1.5 kilometer configured for 3 specific domain over Indian region. I will show the schematic in my next slide. We are using in that NCM based HRDA 4D VAR data assimilation system, and we assimilated conventional satellite radiance and DWR reflectivity and radial velocity from our Indian radar stations. So another is a WRF-based HRR system, nested domain. It cover 5 kilometer whole India, and another mother domain. This second domain is 1 kilometer cover northern part of India. Mostly we are interested over the Indian Western Himalaya region because we are getting lot of this extreme weather event due to climate changes over this region. So we are more focused over that Himalaya region from cloud burst, heavy rain event, and that domain also we have shown in the next slide. And here we are using GSI 3D VAR data assimilation technique. Now we have a planning to in that HRR system 4D VAR ensemble system in future, and conventional satellite radiance and DWR reflective radial velocity only, not reflectivity, because this is a hilly region. So we are not developing that quality of these radars are all X band, so it is a difficult to do. So now work is going on how to incorporate this reflectivity from X radar. So this is the based system we are using at NCMRW. This is a unified model adopted from the UK Met Office. I am not going detail. This is the seamless prediction system from global to high resolution 30 meter Delhi model. So we have a ensemble system. We have a regional ensemble system at 4 kilometer, couple models at 6 kilometer, and my focus is regional 4 kilometer regional model. So based on this regional model, we develop one HRR system over the Indian region. I already talked about in this NCM based HRRDA system, we have a 3 domain. Domain 1 is covered to western part of the India, and domain 2 is eastern, and domain 3 is southern peninsula extend to up to central part of India. This is the schematic of the HRRDA system NCM based, and the grid each box has a 1000 by 1000 is domain, and vertical level is 80 kilometer. Or already we are using 4D VAR 1 hourly rapid refreshes and assimilation system at 1 kilometer resolution. And this is when we have tested this system, we have considered few heavy rainfall event at 3 domains, but here I am showing few of them. One is domain 1, which is called happened over the Mumbai region, that 5th to August 2020. It was very devastating at Mumbai, over the Mumbai city, and another 2 thunderstorm cases over the north region, pre-monsoon thunderstorm and early monsoon active time. So here I am not going detail of the result is why, but it is a emerging system. It can capture the high rainfall. This, if you see, this is the upper line. Upper panel is our observations from IMD, GPM and DWR over the Mumbai region. So we have operational 4 kilometer resolution. So it is operational throughout year. So if you see the operational model is this heavy rainfall is moved maximum over the inland mass, and it is more northward if you see the Mumbai, it is this tip point is Mumbai, so there is no much rainfall over this region. If you have a control, that is a HRR system without reflectivity and radial velocity, and rad is reflectivity and radial velocity, so it is showing that the reflectivity, assimilation, and radial velocity have a positive impact on the extreme rainfall event. And if you see the bottom panel of this time series 1 hourly data, we have a plot of DWR operational and GPM with the control and rad. So if you see the quickly the RMS is reduced in the radial rad experiment, which is good after assimilating of the reflectivity and radial velocity. So quickly move to the two thunderstorm cases over northeast regions. This is 7th June and 9th June over the northeast region. So a lot of lightning and rainfall happen within few hours. So we have a see, then that time only Agartala data is available. So we have a quality control. This is left panel, top of the left panel is our raw observations, and after quality control in our NSUM model, we have a QI. If it is 0 to 1, then this index will be assimilated. And this number of observation we are assimilating on that small domain. And this final, this last one is RMSE of O minus B and O minus A. If you see this figure, the O minus A is reducing as compared to O minus B. But one peculiar thing we have seen, once this reflectivity is assimilation, there is some RMS is in O minus B and O minus B is high as compared to other. So it needs, it give a message. So we need further quality control. It's not well-proved quality control, we can say. So this work is going on. So how will more quality control apply to the reflectivity? And but radial velocity is coming is good. It is reasonable for this RMSE, but for this reflectivity is O minus B, and if O minus A, you can see this is high error. So this special plot is also showing the high resolution HRR system is producing rainfall. If you cannot see this in naked eye, so we have some statistics. So if you see the ETS, and if we can see the different threshold in x-axis and the ETS, so in a lower threshold, the rainfall is good in both the system. And if you go higher threshold, the skill is more in HRR system. So another statistics we did, contingent rain area CR threshold at 10 mm. You can see this first row, and if you see the first column and the second column, case 1 and case 2, in the first row we have a volume, displacement, and pattern error at a different color. You can see HRR, if you have seen the volume, you have get more volume error, but if you see displacement and pattern, it's considerably improved. And in the second row, we have a total mean square error. If you add all this, then this HRR is slightly less as compared to control. And vector displacement error at a degree also showing the HRR as good performance as compared to control. So in bias with at the same threshold 10 millimeter, you can see this is our forecast hour up to 24 hours. In both the cases, we see that after 16 or 18 hours, the reflectivity or radial velocity assimilation system, HRR system, is coming to the control run. So that means it has some impact up to the radar, and observations have up to impact the short forecast, not the longer forecast. This is the message we are getting from HRR system. And this is a distant cloud burst, and this is the what I already told. This is the NSUM based HRR system. Here I am going to our WR based HRR system, because in a NSUM system we are not focusing over this region due to some technical issues. So we have developed one HR system on WRF over the Western Himalaya part, more focus in Western Himalaya region for cloud burst. So you see, this is the very typical interaction from the Bay of Bengal and Arabian Sea moisture and dry air and with the complex terrain. So it is a very difficult phenomena or say physical processes or mechanism over this region. So it is a very typical situation when you have any cloud burst or any heavy extreme events over this. All the models are failure over this region. So we have developed this system over this region, more focus. These are the observation assimilated, and this is the schematic is showing how many observations are assimilated from the radar and other systems. So this is just briefly, I'll say this cloudburst 13th August, 51 people killed within 24 hours, and 14 of them are at only one place at Simla landslide. This is the synoptic, and this is the report published by the government. So many people are died and many people are missing during that time. So if you see, this is 850 hectopascal, 500 hectopascal wind, and this see 850, the wind is coming from the Arabian Sea and the merge with the dry air from the Pakistan, Afghanistan region. It is more clearly seen in the vertical integrated moisture transport. We can see. So this vertical moisture integrated is showing high moisture is accumulated over these hilly regions, and it is pumping from the Arabian Sea and interact with the dry air from the this western part of the country, Pakistan and Afghanistan region. So this 13 August 2023 at a 14 UTC when the cloudburst was occurred from the HRR system, we already have a 5 kilometer and 1 kilometer. Both are the HRM system. This is the mother domain 5 kilometer, and this is the second domain 1 kilometer. So if you see, 1 kilometer has more prominent features as compared to the 5 kilometer, and this is the features and the pattern and the vertical extension of this event convection is highly and horizontal extension is more, and it is comparable with the radar and this our satellite pictures. So if you have a 24-hour merge rainfall, if day one forecast we consider, so this left panel is a GPM merge, and the middle one is 5 kilometer, and last one is 1 kilometer. You can see the rainfall over these two patches where the heavy rain was occur is well brought out in the both the system, but the amount is high over the HRS 1 kilometer. So certain patches also missing in both the system, but the 1 kilometer HRR system is reliable as compared to 5 kilometer. So here it is a last bottom panel is showing the time series of the rainfall, but here is lacuna is the second peak of rainfall. None of the model is picking the second rainfall, and if you have see the exact time bound, and it is 1 hour lag of rainfall, but the amount of rainfall is well comparable with the GPM from the 1 kilometer. So here we also seen the more statistics for CRA 5 kilometer and 1 kilometer. If you see the text, you can easily find out what is the difference between and how the performance of a 1 kilometer HRR system is performing with respect to 5 kilometer. It is clearly showing the RMS is reduced, and also displacement error is also reduced, volume error also reduced around 1 to 2%, and the pattern error also reduced, and the degree of displacement also comparatively reduced 0.1 degree north, and around 6 degree on east. So it is this message is, yeah. I just this is my last slide. So this message is, if you have a high resolution HRR system over this region, and it has a capable to pick the rainfall, but certain cases also this heavy rainfall is missing because we are not able to assimilate high spatial and temporal observation and reflectivity. So now work is going on how to assimilate the reflectivity over that region. Around 5 to 7 radar is there. So reflectivity, we are these are the X band. So S band and C band, there is no issue, but X band have a certain quality control issue. So we are now developing. So hopefully in the next 1 or 15 days, we are able to assimilate and get a good result in this aspect. Thank you. If I have any question, then I can answer. Happy to answer.
Thank you very much for this very interesting talk. We already have 2 questions in the UPad. So there's one question by Maria Dillon. What kind of cycling do you use for your rapid refresh systems? Partial or continuous cycling?
Yes, it is a continuous cycling, and every 1 hourly we have an update, and each hourly then we have a 18-hour forecast. So up to 24-hour cycling we are doing. Then after 24 hours again we start the cold start. But 1 hourly we have a cycling, and each 1 hour they have a 18-hour forecast. And this WR based system is operational now. But NCM based system is a test mode, so it is taking a lot of time because it's huge computing power. So next computing facility we are going to operationalize that. And second, what is the second question?
Yeah, the question, a second question is by Lars Nerger. And he's asking, at the beginning, you described that you use a 40 bar with 1 hour assimilation window. How frequent are the observations that you assimilate? And what is the computing time to complete a 40 bar cycle over the 1 hour window?
So in this case is okay, 1 hourly observation. So we are assimilating, and 3-minute window is plus minus 3 for the radar. So mostly more focus in the radar reflectivity and radial velocity. So in the small domain, we are not getting much of the observation in synoptic and this conventional, but more focus in radiance and this radar reflectivity and radial velocity plus minus 3 window. And it is taking exactly, I cannot, but it is taking 2 to 3 hour forecast from start to end. 2 hour, maximum 2 hours, we can say.
Okay, great. Thank you very much. Then I think we go on to the second talk of today.
Okay, thank you.